Okay, right. The tech is somehow working. Okay.
Yeah,
Our final
amazing.
speaker for the entire ACT is Sean Tull. We'll talk about explainable AI. Take it away.
Right, thanks very much. Thank you, everyone. Feel free to adjust the volume a bit or something if you can't hear me okay in there. Um, Thanks for sticking around for the last talk. And yes, I'm very sorry I can't be there in person. I went down with something right at the beginning of the week, and I've been hoping each day that I could get into the conference, but I've had to just been watching online in the end, unfortunately. Luckily, as it's the last talk, it's not going to be too technical. It's going to be more of a conceptual talk, this one. So I'm going to be talking about this problem of interpretability in AI, and this is going to be joint work with Robin Lorenz, Stephen Clark, and also overseen both by Bob Coecke and Ilyas Khan, all at Continuum. So I'll just get into it, I think. So the motivation is that obviously AI models today are very powerful, but they lack this feature of interpretability, meaning it's hard to understand how and why they produce the outputs they produce or how exactly they work. And that's fine in a lot of situations, but in certain areas, like high stakes areas, they're known like the finance or the health sector, you really need accountability for your models. And so this is considered a big problem. So for an interpretable model, we'd like to be able to answer questions like how it works, maybe determine whether it's biased or trustworthy, or maybe understand why it gives particular outputs and not other ones. So there's now a field called explainable artificial intelligence, or XAI, that's trying to address this. And so far, the way that it does this is mostly focusing on what are called post hoc techniques, where you take a trained model, and mostly what you're doing is explaining particular outputs of the model in terms of different inputs. So for example, you have things that are called counterfactual explanations, where you'll say, how could I slightly tweak my input to get a completely different answer? Or you'd have salience maps where you kind of value how important some pixel was or some feature was to an output. So these are just kind of looking at inputs and saying, how do they affect the output? So it's early days in this field, and these methods have been criticized a bit. So for example, by Cynthia Rudin, who points out this example with salience maps at the bottom, where when you apply them to an image where it's given the wrong classification. So here we see a salience map for why this picture of a dog is in fact a flute. You still get one of these maps. So they're telling you where the model's looking, but they're not really quite telling you how or why it works. So you might like a deeper kind of explanation. As well as this, there's just conceptual issues in the field, like there's no real completely fixed notion of what interpretability or an explanation is, just lots of examples. So we wondered if a categorical perspective can be helpful here. And the second main motivation for thinking categorically is that there's an intuition that certain kinds of compositionally structured models should be more interpretable than others. Some examples of these would be causal models, which have been studied a lot at ACT. This is a string diagram from a causal model, or things like disco models in NLP, which we just heard a bit about, the disco cat versions of, rather. And these are both kinds of models we've looked at in this compositional intelligence team of Continuum in Oxford. So I've put our little logo here. So we kind of have this intuition, but how do we make it precise? In particular, if you think about it a bit, then something like a neural network is compositional, right? So it can't be everything you need. So that's the point of this work, really, is trying to firstly, we give a kind of categorical approach to just defining AI models and what an interpretation is or interpretability is. And then we see that from this perspective, how can we kind of make sense of the fact that some compositional structure should help you get more explainable models? So I'll get into the theory now. I think Alexis already introduced monoidal signatures earlier, which is nice. And this will be our starting point for what we're doing. So we're going to be defining a general framework for treating AI models now, just as what we call compositional models. And on the structure side, a compositional model will start from a signature. So that's a set of formal objects, which we'll call variables, a set of formal morphisms, which have like lists of inputs and outputs. But we'll call these generators most of the time. And we also allow you to have equations between diagrams built from these generators, but that won't be too important here. And essentially what you do is you take this signature and you pick a sort of diagrammatic language you're working with. So for most models, we'll talk about something like CD categories enough, where you have copying maps and discard maps, let's say. But you could just be working with plain monoidal categories. Whatever you choose, you can then build this free category that we call S. We call the structure category of your model. So this is the category of all diagrams we can build from our variables and generators. And this is the structure or syntax side of our model. And then a compositional model is going to be a functor into a semantics category that implements it. So it's just a standard categorical logic kind of picture of what a model should be. And we refer to this functor as the representation. Often it would be called an interpretation in mathematics, but that's a bit confusing in this context. So just as an example quickly, so if we had our signature in the bottom left, and let's say we were using the language of CD categories, these copy discard categories, then the generators could be something like this. So we'd have variables A, B, C, D, E here, and these generators lowercase a, lowercase b, lowercase c. And then from that, we could build this free category of diagrams, this S category, and that would contain some of these would be morphisms in that category. So for example, the one on the right here would be a morphism from the list ABC to the list DE, and it would represent this string diagram. And the model basically just gives the semantics to each of the generators and therefore to any diagram as well. So it ends up as a functor. We'll see lots of examples of these in a second. Before that, I'll just talk about how we treat interpretations in this picture. So because we're talking about interpretability here, we're talking about interpretations of models in the sense of like making human sense of them. And actually, there'll be two aspects to what an interpretation is in our picture. So firstly, there's what we call the abstract interpretations. This is something you just apply on the syntax side. So you just apply it to the signature, the variables and generators. So for example, we might have a variable, V, and we think of it as representing brightness of an image or something like this. Secondly, we might want to interpret parts of the semantics itself separately. So we'll have a mapping called the concrete interpretation, which does this. And this interprets specific morphisms in the implementation category. Mainly, we're thinking of states most of the time when we do this. So for example, if we're saying that we have a variable V, and let's say it's like a normal classical kind of model where it's mapped to the real numbers as its implementation. If we say that V corresponds to brightness, we probably mean something like, well, 0 means dark, and higher real numbers mean more bright. Say 1 means very bright or something. So you wouldn't have a generator for every possible state, every real number. So you need to talk about the actual semantics as well and interpreting that. And that's the function of the concrete interpretation. So that's the basic idea. Formally, what we do is we define an interpretation of a model in the following way. So basically, we ask for a collection of human-friendly concepts, and we don't formalize what it means for something to be a human-friendly concept. That's maybe some other work to do in future, or it's just up to the situation at hand. We just ask they're organized into a signature. That just means, we have interpretations for objects and interpretations for morphisms with types separately, but we don't necessarily have composition or anything. So it's not too strong a requirement, really. And then we have these abstract and concrete interpretations I mentioned, and formally they form maps of signatures, meaning they map generating objects, which we call variables, to variables, and generators to generators in respecting types. And they're such that this diagram below would commute, which I'll explain in a second. In general, they're only partial. So it could be that you have parts of your theory, of your compositional model. So it could be in the generators or it could be in the semantics that you can't interpret. Normally, most of the semantics, in fact, you can't interpret. You don't expect to give a meaning to every possible morphism going on there. Even some of your generators you might not interpret either. So these are partial maps in general. And they have this diagram that commutes that just says they respect each other essentially. But I haven't explained what this CG is. I'll just get to that first. So essentially, you'd like to define the concrete interpretation on C, your semantics category itself. But really, you need to know what variable you're talking about when you interpret something. So if you imagine you could have two variables that both get mapped to the real numbers. So there isn't just a general interpretation of the state 0. It depends which variable we're thinking about. And we just capture that by slightly altering the category C, our semantics category, to include generators, include the variables indexing the morphisms, essentially. More importantly, just the main idea is that these are partial mappings. Abstract applies just on the generators and the variables, and concrete applies on the implementation side. And we'll often talk about something having an abstract interpretation, meaning this map IA is defined on it. And we'll say a variable has a concrete interpretation when all of its states have this map IC defined on them. So in this brightness example, it would mean we can make sense of what every real number means in terms of brightness. In the paper, we use this setup to talk about a really long list of different examples of AI models, and I'll just go through them really quickly to give a feeling of how it works. In each case, I'll just draw a string diagram, which basically implicitly encodes all the generators and the semantics for the model. And I will just talk about which parts have an interpretation or not. I won't spell out these whole maps every time. So to get started, we could look at just something like neural networks themselves. So you could view an individual neuron as a compositional model like this, where you're working in this category of functions between sets of the form R to the N. So and moreover, you would ask that each wire actually has semantics as the real numbers. So you'd have n different real inputs here. And you're multiplying each by a weight, adding this bias, and then applying this nonlinearity here. So formally, you'd have generators. You'd have variables for each of the inputs and the output, and generators for the weights, which would appear in this multiplication morphism, which is what this box means, and for the bias. And you could formally treat, and for the nonlinearity, sorry, and the rest would have a fixed semantics. So you could treat it as a generator, but this has to go to the plus map, for example. More generally, you can stack these together to build neural networks, right? So you can describe these as compositional models as well, where now each of these gray dots would be like a neuron with its own weights and biases, and you just copy the outputs and pass them to each other in layers. Similarly, you could have whole architectures described as string diagrams. So you could do something like a transformer, where you can draw a string diagram for the whole thing. The details won't be too important here, but H's would correspond to the attention heads in a transformer. And they would also have a specific semantics, but you could break it down in terms of this variables and generators picture that we set up. So formally, these just general black box kind of neural networks can be described as compositional models in our sense. But this doesn't mean they're... So first key point there is that you do have this kind of compositionality in machine learning as it's currently done. It's not a new idea itself. And also it's clear that it doesn't imply interpretability. So for a neuron, a generic neuron in a neural network, you don't really know what each input or output means at all. Particularly in a network, you might often know what the inputs and outputs mean. So they would have normally a concrete interpretation. So the inputs and outputs would relate to your data, and they would have a concrete interpretation. So you know what each wire means and what each of its states means. But for the layers in the middle, you probably wouldn't have any abstract or concrete interpretation. You just don't know what they mean. And similarly for a transformer, you don't a priori know what each attention head means. So most of the XAI stuff is about doing further stuff to try and work out what these things mean, but you don't know it a priori. So you can have some structure, but it doesn't mean you have interpretability. So that's why we've separated the two notions out. Yeah, and typically you see only the inputs and outputs of these models are interpretable, and that's where XAI methods often focus, as I mentioned at the beginning. So what models would be considered more interpretable typically? There's a class of models called intrinsically interpretable models that people often study that basically consist of linear models and types of logical or rule-based models, they're known as. So again, we can describe these formally as compositional models. The linear model looks just like the neuron that we saw, but without the nonlinearity at the top. So formally, it's pretty much the same thing, right? So the difference in interpretability is just that this is the whole model. So in particular, the x1 to xn are the actual inputs. They're like your data set or something. And the y are the outputs. And those would normally actually have a complete concrete interpretation because they relate to the task at hand. There's no hidden layers in the middle, basically. More clear, I think, are those kind of rule-based or logical models in terms of interpretability. So this is a decision tree model that we show in a string diagram on the right. And you can just think of this as being in the category of sets and functions. So the input would be data about someone applying for a loan. And then you have questions that branch in this tree. Are they homeowner? Are they employed, etc. And then basically you can give semantics to a diagram like this that does actually implement the decision tree, meaning only one of these paths will have all yeses come out of it. And that will end up being the output here at the top. So for each wire, in this model, there would actually just be one variable for this wire and one variable for the output. And the y ends here are just convenient labels. And you can give it a semantics to the boxes where they do ask these intuitive questions of the data, like are they a homeowner, are they employed, etc. So here, everything has a very clear, concrete interpretation. We'd know exactly what the states mean coming in the data, and we know what all these questions mean. And what's nice also is that the way that these models are normally considered to be intrinsically interpretable is diagrammatic in the sense that the string diagram you draw, if you want to describe these models, contains the things that normally is considered to make them interpretable. So you see the tree and you see the conditions when you draw the decision tree out with a string diagram. And for a linear model, you see the weights, which are interpreted as normally importance of a feature to the output. So these fit nicely with our setup is the conclusion, and it encourages us to slightly broaden the idea of what kind of models could be considered interpretable. So we call a model in this work compositionally interpretable when it has an abstract interpretation or a complete abstract interpretation, meaning every part of the signature, so all of the variables of the model and all of the generating morphisms, they all have abstract interpretations at least. And it's even better if they have concrete interpretations too, but that's not required for this definition. So intrinsically interpretable models, the usual examples of interpretable models in AI, are a special case. There's also other examples. So on the left, for example, you can see something like a recurrent neural network at a certain level of abstraction as meeting this definition. So because I'm doing diagrams bottom to top, it reads bottom to top, so the text looks a bit funny. But this is for a text, for example, like Alice says hello. Each word, so in an RNN, you'd have one variable only for the wire, which is just your general meaning space. And then you would just have a generator for each word that gets mapped to a neural network in the implementation. But you know it has an abstract interpretation. It corresponds to that word. So every part of the model is abstractly interpreted in that sense. A more sophisticated version compositionally of the same thing would be something like a disco circ model, where now, again, you have words corresponding to boxes, but now you can have multiple wires corresponding to the discourse reference in a text. So these will have abstract interpretations. And then you have each word is represented, would be a generator, and it's represented either by a box or more generally by a higher order process. So that takes a little bit more formal work to make really precise, but it's the same idea as the way we treated signatures earlier. So you can treat each word like sober or sees here as a box or generally a higher order box, similarly to what we saw in Alexis's talk. And they all have abstract interpretations as well. The final example would be something like causal models, which have been studied a lot in both the ACT community and also in machine learning. They're one of the kinds of structured models that people do think about in this area known as causal machine learning. So this is a network diagram describing a causal model. So here you have a variable for each variable of the causal model and a generator corresponding to the mechanism for each variable that we see here. So from these examples, you can see, okay, they all fit this definition. All you need is an abstract interpretation, but you might think some of them are more rich than others. Like you might think disco circ lets you do a bit more than just the RNN type of composition. So we've started trying to think about that question, but we haven't formalized it yet. So I think this is an area for future work as well. The way you address this is you might want to talk about how rich the compositional structure of your theory is. We can capture that with a notion we call the compositional framework. The framework describes what you can do with your model. So the model itself is just your generators and their implementation, their semantics. But it doesn't tell you, okay, but which kind of, what do you actually do with these things in practice? Like what morphisms and diagrams do you actually build from them and use? So you capture that by saying what framework you're considering the model in. The simplest example of framework would just be what we call an input-output model, where you just have one black box, this M for model. You can plug inputs in, and you can look at the output and maybe marginalize the outputs, and that's it. So that's just like a generic black box trivial framework. A bit more structured would be something like the framework of statistical models, where now we know that our wires have some kind of probabilistic semantics, and we can think about things like probabilistic conditioning. So this is a string diagram for computing a conditional from our model. And famously more elaborate than this would be the framework of causal models, which is known to let you go beyond what you can do with statistical models. So you have a causal model, you have all the generators, but you also know that you can do meaningful things with them, such as computing what are called interventions, where you reach in and alter the string diagram for your model. And also if you have the right kind of causal model, what are called counterfactuals, which we see in the diagram at the bottom. So the idea is that the framework of causal models is basically a richer one. It includes what you can do with statistical models, and they include what you can do with input-output models. And you could similarly try and talk about frameworks for different kinds of NLP models and so on. But now I think I'd like to come back to more to the motivation for the talk at the beginning. Excuse me, sorry. So I suggested that this idea of a CI model, this compositionally interpretable model, would capture this intuition from the start of how a compositional structure can give you more explainability. And we wanted to make that more precise and talk about what kind of explanations you can actually get out of a CI model. So in the paper, we talk about 3 ways of getting like specific types of explanation techniques from a CI model. What's nice is that they're all purely diagrammatic. So you only need this abstract interpretation, so you can actually apply them to classical models or other implementations, like quantum implementations, which I haven't really talked about so far. But if your model doesn't use copying or discarding, for example, it could just as easily work with a quantum one. So I'll briefly talk about the first 2 and then maybe slightly more time on the third one of these techniques. The first thing you can do with a CI model is just talk about influence relations. So you have a model that's based on channels, meaning you have discarding in your category, and you can pull that through all the boxes. Then you can talk about signaling, as we've heard about in other talks this week. So in particular, you can just look at a string diagram for your model and often deduce a lot of signaling relations or influence relations from the inputs to the outputs. So if we know our model takes this form at the bottom left, we know that, for example, A won't be able to influence D if everything here is a channel, and here is the diagrammatic proof. Often this is very easy to do just by looking at the diagram. But no, it's not possible to do this with something like a fully connected neural network, where you would have wires going between all the inputs and all the outputs. So it does actually require non-trivial compositional structure to be there in place. The second kind of explanation technique I mentioned briefly is what we call diagram surgery. And this is a term that was already used for causal interventions by Jacobs, Kissinger and co. a while ago. So essentially, from this view, you're slightly extending the view of just acting on inputs that you would normally do with XAI techniques to now think about boxes inside your model. So if you have a compositional model drawn as a string diagram where you have an abstract interpretation for every piece of it, you can often act on the diagram by changing some box inside it, and this will be meaningful to you as well. So causal interventions are one example of this. And yeah, more generally, you can think of it as a bit like a counterfactual explanation, where you're tweaking the inputs, but now you're not just tweaking inputs, you're tweaking what's going on inside. The final kind, which I'll spend slightly more time on, is what we call a rewrite explanation. So let's suppose we have a model, we give it some input and it produces some output. And we like to explain that particular output. More generally, we could just have 2 diagrams that come from our model that we want to explain. So a rewrite explanation consists of a collection of equations between other diagrams and a proof that if you use these, you can derive your first equality that you wanted to explain. So for example, we have this picture here, we have a model F, and what we do is we first use an equation that lets us decompose it. Say we know this is the shape of our model. Then we rewrite some parts of it, and we keep going until we get the output Y that we wanted. So you could always do this. For example, you could do this with a neural network, just plug the real numbers in and pass everything through. So to make this feel like an explanation, it needs to be that all the diagrams you're looking at the whole process are fully interpreted. So either they consist of generators with an abstract interpretation or say states with a concrete interpretation. If that's the case, then that's like a sort of minimal condition for this to feel like an explanation. And it's a bit open whether you need more conditions than that for it to really feel explanatory, but that's a minimal you would need. If you have some pieces in the diagram so you don't know what they mean, it's going to be very hard to convince someone that this is a good explanation for its behavior. But if you do give a set of these interpreted diagrams and you use them to give a proof, we can see this is a kind of explanation of how this equality occurs. So for an example, let's suppose we have an RNN and it's giving employed homeowners, it's asked whether to give people a loan, and it seems to always do it when someone's an employed homeowner. So let's say we observe that it has these 2 equations. So if we put homeowner employed in to the model, we get that they're equal to some state that we can interpret as sort of reliable, a reliable person. And secondly, that if we ask whether a reliable person should get a loan, this is approximately equal to the answer yes from the model. Okay, then we plug these together and we can get a proof that if we have an employed homeowner, we ask, we're going to get yes. So this is basically the simplest possible form of rewrite explanation because we're just using sequential composition on a line. Now, it might seem totally trivial. You couldn't do this kind of thing with a generic black box. So if you had a transformer or something, where you had the equivalent of the first two equations, there's no structure that's helping you put these two facts together to deduce the last one. So even if you know that it thinks employed homeowners are reliable and that reliable people should get loans, you don't know that it's going to give employed homeowners loans. So this is the feature of a kind of the sequential composition in the RNN example. A slightly more elaborate version of this would be like a DiscoCirc type problem, and where you could have rewrite explanations for these. This is kind of an upgrade of the RNN example. So suppose we have some text that says Alice is with Bob, Bob is in the garden, where is Alice? And suppose our model is set up so that we have some equations between words. So in DiscoCirc, each word will be, in this case, it'll just be gates acting on wires that correspond to the nouns on which they're relevant. So this first equation says, if we say that one person is with another person and we ask where the first person is, it's the same as wherever the second person is. And similarly, if we say they're in some location and we ask where they are, well, it's the same as wherever that location is. So that's what these two equations say. If we have those, then we can kind of explain why, given this text, we would always the answer would always be the same location as where the garden is. So the text would correspond to this diagram down here. We've got Alice, Bob, and garden. Alice is with Bob, and Bob is in the garden. And we ask where Alice is. We apply our interpreted equations from the top to rewrite, and we'll get to this right bottom picture, where the answer is just wherever the garden is. So the question is whether you can build enough sophisticated models that do come with axioms like this, so that in practice you can actually use this to get explanations out of your model. But you can see that if you do have some interpreted equations between components in a compositional model, you can start reasoning about them and get these kind of constraints on behavior and so on that you can interpret. So yeah, and I'll start to wrap up now. So I talked about quite a lot of stuff. What we basically do is try to give, we're trying to show how an ACT type perspective can be beneficial in this whole XAI topic. In particular, showing how you can define a lot of AI models in terms of string diagrams and give formal definitions to notions like interpretability. This led us to think about these models that we called compositionally interpretable, and we explained how they can give certain types of diagrammatic explanations for what they do, so you can actually prove constraints on their behavior. There's loads of stuff you can do in future. Very quickly, this rewrite explanation idea, for example, should really be sharpened a bit more. Can you get lots of nice models which actually have these equations? If so, then it should become like a whole XAI tool with software and so on for automating the explanations. In general, it'd be nice to give more interesting examples of these CI models. We mainly just talk about disco models and causal models in this work, but it'd be good to grow that set. There's clearly a big space of further CI models to think about. For this, it could involve solving this problem of generally how do we go from raw data to actually learning compositional structure. So in the area of causal machine learning, this is called causal representation learning. And more generally, we could think of this as a kind of compositional representation learning. One way that this could perhaps be done is by going from a typical model like a neural network and then relating it to some high-level interpreted compositional model. And an intriguing approach to doing that for causal models is called causal abstraction. And that's something we'd like to look at in future and see if maybe you can also extend it to further kinds of compositional models. Okay, thanks very much for watching this, especially online, and the last talk of the day. Thank you, everyone.
Okay. Hopefully you saw and had some of the others. Questions? Okay, I'm gonna. Yeah, this one's fun. Good luck. Thank you.
Hi.
I was just curious if type systems played a role in the future work that you were suggesting.
Oh, which point in particular are you thinking of? Any of
Right,
these
more
4
like
points?
learning the structure, like type rewrite system.
Yeah, maybe we should. I don't know. I'd be curious to know what you think about it. It's not something we'd thought about yet. I mean, it's a huge problem. I think this issue of how you actually learn the structure, but we are ultimately talking about, getting from raw data to types in some form. I mean, I think that's what it would mean really to go to something like a causal model. But I haven't thought about, more sophisticated types of type constructions and things like that at any point yet. But even just going from data to learning like meaningful variables at all that you can separate it out, it's a big area that I think a lot of machine learning will want to look at now. But it'd be obviously great to have like richer type information while you do that. Yeah.
Thank you.
Thanks.
Any other questions? And this time I'll repeat the question. Oh, okay.
Thank you for the talk.
Hi.
Sorry, there's something I misunderstood, I think, at some point. You gave an example with RNN, which didn't work for transformers, but I don't understand why it would, like, what's the difference between the two that makes it not work for transformer, but work for RNN?
Yeah. So this was the example, yeah. So with an RNN, I mean, I've skipped details in the sense of you're assuming you have a notion of approximate equations that behaves well compositionally, but maybe let's just assume these are strict equalities. In that case, you can literally plug these equations together and prove it for the RNN. So hopefully that's okay.
Oh, sorry. Yeah. Oh, sorry. Continue.
Yeah, and for the transformer, I mean, here there's literally no way to do it because, the diagram in the equation just has a different box, right? It's got this free wire based box. So for a transformer, you'd use like a different sized one for something with 3 inputs. So it doesn't look formally the same. But even intuitively, I think there's no like guarantees in the way transformer works that it will have that kind of associativity. You can't really just like, you don't like apply a transformer to 2 and then apply it to the third one or something like this. So you can't really conclude just from the knowledge about these 2 inputs what state that gives, how that will behave when you add another word in. And I'm sure people would argue that this is like a strength in the sense of it leads to like more contextual kind of representation or something like this. But it does also make it harder to prove guarantees. Like you don't expect to be able to prove something strict like this. Thanks.
Yeah, thank you.
Thank you.
Okay, I think we've overrun a bit, so
yeah.
Sorry. Yeah, I think we should stop. Let's thank John again.
Thank you, everyone.